Hello, Anacortes High School Geometry. Welcome to week 6 of new content. Today we're going to keep working with circles, and specifically we're going to talk about the interaction between angles, arcs, and areas. Okay. If you recall from last week, an arc of a circle is basically a section of the curve of the circle. In this case, if I've got a 90-degree central angle, the curve in between the two endpoints would represent the arc that we would be talking about. Okay. And we talk about arcs in two ways. First off, we say that an arc has a measure, okay? And an arc measure is basically indicating how much or how large the central angle is that forms it. This central angle is 90 degrees, so we would say that the measure of this arc is 90 degrees, okay? And we like to say that arcs have measures because it doesn't matter how big or small the circle is, as long as that central angle is 90 degrees, this arc measure will also be 90 degrees. All right, now something that does depend on how big or small the circle is the arc length. And that's the distance that we travel along the curve in between the two endpoints. So imagine if you were walking or driving along this curve, how far do you go? Not in a straight line, but how far do you travel along the curve from one endpoint to the other? Okay, so how can we use things that we already know in order to find an arc length? Okay, well, one thing that we know a lot about when it comes to circles is the circumference. We find the circumference by multiplying the radius by 2 pi. Okay, well, what is this arc length going to be? I think the real question to consider is how much of the circumference are we using for this particular arc, okay? All right, now this example has the 90-degree angle, and most of you would look at this circle and say, hey, that's a quarter of the circle. The arc length is going to be a quarter of the circle's circumference. And you'd be right. We would take the circumference of this circle, which is equal to 2 times pi times 4, okay? So 8 pi, and we would multiply it by 1/4 or divide by 4, and we would get an arc length of 2 pi. Okay, that's pretty intuitive and it should make a lot of sense to us. But what if things are a little bit trickier? What if we look at the circle and the central angle and the arc it creates doesn't make something obvious like a quarter or half of a circle? Okay, well, how much of the circle does this arc represent? Well, how much of a full rotation does 100 degrees represent? It's 360 degrees to rotate all the way around, and this angle represents 100 degrees of rotation. So this represents 100 out of 360, just like 90 represented 90 out of 360, which reduces down to 1/4. It's a quarter of the circle. 100 360 doesn't have any fancy name, but we can reduce it down to 5/18, right? 20 goes into both 100 and 360. So 100 divided by 360 is equal to 5/18. So our arc length is going to be the circumference of the circle, which we have already established to be 8 pi, times 5/18, because that's how much of the circumference we want. We want 5/18 of it. Well, if I multiply these together, I can think of 8 pi as being over 1, and I want to multiply numerator times numerator and denominator times denominator. So 8 pi times 5 is 40 pi, and 18 times 1 is 18. 40/18 reduces to 20/9, okay? So the exact arc length that we see in this circle above is 20 pi/9. To generalize what we just did, how did we find the arc length? We took the circumference of the circle, we multiplied it by the central angle divided by 360, okay? Or a reduced down version of that fraction. Well, to simplify it even further, we know that the circumference of the circle is always going to get multiplied by the central angle in the numerator, and the circumference is 2 pi r, and 2/360 reduces to 1/180. So the most reduced version of this formula is going to be pi times r times the central angle divided by 180. All right, what if we wanted to find the area of a slice of our circle? We call that a sector. Well, the same idea applies. If I look at this circle, I see that this sector represents a quarter of the circle. So I would take the area of the circle, which we get by doing pi times the radius squared. So in this case, I square the radius, to get 16 and multiply by pi. So the area is equal to 16 pi. And I want a quarter of that. I'm going to divide it by 4. I end up with 4 pi as the area of that sector. Once again, what do we do if it's a little bit trickier? If the sector we're looking at isn't something obvious like a quarter or a half? Well, the same idea as before applies. How much of the area of this circle do I want? I want 100/360ths of it, or 5/18ths, because 100 over 360 reduces to 5/18ths. Well, our sector area is just going to be equal to the area of the circle times how much of the circle we want. Okay, we want 5/18ths of it. So in this case, 16 pi times 5/18ths is going to be 80 pi over 18. 80 divided by 18 reduces to 40 over 9. So 40 pi over 9. To generalize what we did, to find the sector area, we took the area of the circle, multiplied it by the central angle, and divided by 360. And the area of the circle we get with pi r squared. So sector area is equal to pi r squared times the central angle divided by 360. All right, now central angles aren't the only kinds of angles that we've worked with when it comes to circles. We've also talked about something called inscribed angles, where the vertex of the angle is on the circle itself. What if I wanted to find this arc length? Okay, I don't know what the central angle is. I just know that this inscribed angle is 62 degrees. If I look at this central angle, the fact that one endpoint would be up at the top and the other is down here, like below this horizontal radius segment that I've sketched in, I would say, hang on, the central angle is obviously not 62 degrees. Can we use some things we know about triangles and quadrilaterals to maybe figure out the relationship between this inscribed angle and the central angle that would have the same two endpoints? So let's start with an equilateral triangle. An equilateral triangle is a triangle where all three angle measures are 60 degrees. So I've got 60 degrees and it's creating three arcs. This 60-degree angle is creating this arc on the other side of the circle, right? Because the endpoints of this 60-degree angle are at the top and the lower left. So the arc that the lower right 60-degree angle creates is right here. The lower left 60-degree angle is creating the upper right-hand arc, and the top 60-degree angle is creating the bottom arc. All right. Okay, well, what if I create central angles that have the same endpoints? So for this lower right-hand triangle angle, the blue angle, it has endpoints at the top and lower left. So if I create radiuses from the center to the top and to that lower left point, I end up with this central angle right here. Okay, if I do the same for the other two angles of the triangle, I end up with my three central angles here, here, and here. And I can see that they fill up all of the rotation at the center of the circle. Now, we know that it's 360 degrees to go all the way around the triangle, and these three angles add up to 360 degrees because they fill up all of that rotation. Okay, now since all three inscribed angles, and those are the angles in blue created by the triangle, we know that all three of them are 60 degrees. We know that all three arc lengths have to be the same. If all three arc lengths are the same, that means all three central angles are the same. So I have three angles, they add to 360 degrees. 360 divided by 3 is 120. Okay, so what's our initial impression here? Well, our initial impression is that the central angle, 120 degrees, is double the inscribed angle, 60 degrees, when they have the same endpoints. Okay, that's one example. I need a little bit more convincing. So let's try the same thing with a square. Let's inscribe a square inside of a circle, and let's examine what happens with just one of the angles. So let's look at this angle in the lower right-hand corner. Here's the vertex, and the endpoints are in orange. Okay, if I create radiuses from the center to those two endpoints, what do I end up with? Well, I end up with a straight segment, and a straight segment has a 180-degree angle. So I have an inscribed angle of 90 degrees and a central angle of exactly double it again. So what relationship do we see between central angles and inscribed angles? Well, I see that central angles are equal to 2 times the inscribed angle that has the same endpoints. If I start with an inscribed angle and I want or if I start with a central angle and I want the inscribed angle, I just take that central angle and divide by 2. So a central angle is equal to 2 times an inscribed angle, and an inscribed angle is equal to a central angle divided by 2. All right, so let's bring this back full circle and examine the problem we were looking at before. How can I use this 62-degree inscribed angle to find this arc length? Okay, well, I know that the central angle that has the same 2 endpoints as this inscribed angle, and therefore has the same 2 endpoints as this arc, has got to be double 62, which would be 124 degrees. Okay, once I have that central angle, I can use the same formula we used earlier to find this arc length. Okay, I can also take my arc length formula from earlier and adapt it. So I have just a really clear and concise arc length formula if I have an inscribed angle to start with. So we saw that an arc length is equal to pi times r times a central angle divided by 180. But I know that a central angle is equal to 2 times an inscribed angle. Okay, so I just replace central angle with 2 times an inscribed angle. Well, 2 divided by 180 reduces to 1 over 90, so I can simplify this even further to the arc length being equal to pi times the radius times the inscribed angle divided by 90. All right, there should be some good practice to go along with these new concepts that you can work on this week, and a quiz on Friday. As always, if you have any questions, feel free to contact your geometry teacher. Enjoy and good luck.